To be able to develop a formal understanding of quantum Hall effect, there are several concepts that I have to introduce. So that's what I have been doing so far. One of the things that we have done was studying the Landau levels. And basically this is, in essence, quantization of orbitals that electrons take under the magnetic field. Okay, and what we have done is we have written the Hamiltonian for the Schrödinger equation, and as it turns out, we have to write it in this way, where this is the vector potential for the magnetic field, and we ended up writing the momentum expression this way because we realized, if you remember, that the electromagnetic fields carry momentum themselves. So the mechanical momentum plus that vector potential forms the total momentum of the field. Then what we did is we assumed that I have a magnetic field B pointing in the z-hat direction, and it's a uniform magnetic field throughout my sample. So I have now we restrict ourselves to a two-dimensional electron gas. We could work with a three-dimensional object, but it turns out for technical reasons, most of or all of the Hall effect experiments, quantum Hall effect experiments and discoveries of these Landau levels and so on are preferentially done into the electron gas systems. But it doesn't matter, that's a technicality for now because we are dealing with an ideal system, if you like. So I have this magnetic field, and then what we did is, okay, I have a length Ly and Lx for this electron gas. Then we solved for the Schrödinger equation for such a system. And if you remember, we have written our vector potential as such. So we said, okay, this is actually one of the ways of writing the vector potential. So it's going to be By xhat. And if you remember, magnetic field was given by such an expression, okay? And so what I do to find an appropriate A that can give to a B in specific form was something like this. So I'm going to have my AX, AY, AZ. And to find each component, for xhat component, I take the determinant of this portion. So del by del Y, AZ minus del by del X, AY was the X component of the resulting vector. Y hat would be, again, I take the determinant by blocking this portion. So del by del X, AZ minus del by, sorry, this is Z. Did I make a mistake there? Then yes. So this is Z as well. Sorry. So I'm doing this one. Then del by del Z, AX, And finally, for the z hat component, I take the determinant of this portion. So I'm going to have del y del x ay minus del y del y ax. And since I have a magnetic field that points along the z hat direction, other parts are essentially 0. Okay, so I assign 0 to these guys. And then this should be equal to my b. And as you can see, there are multiple ways of writing b. One option is to say I have, for my ay, I have b x. So when I take the derivative with respect to x, I'll get a b. Then I can write b over 2x, b over 2 minus b over 2 y. So my a vector can be something like this. I have x hat with a minus sign, b over 2 y, plus y hat, b over 2 x. And if you plug it in, you will see that. Is it? Okay. Let me write it over here. So z hat del ay ax del ax del y. Okay. So my a vector is can be composed of 3 components, but obviously I need the x component and y component for a magnetic field pointing in the z direction. Okay, so this is, if you like, ax, this is ay, this is az. So for ay, I can have b over 2 x, and for this one, minus b over 2 y. This is one way of writing, but then I have to deal with this vector that points in x and y directions. So I say, okay, let's be wise to reduce the number of calculations. Let's use something like this, like the one that I've written for the first. Okay, so I can have something like this, and this will simplify my algebra. And equivalently, I could have worked with something like this. So I would ended up with the exact same result, regardless of what I use, because this is, if you like, an arbitrary choice, and it shouldn't affect the end result of the physical system. So just for general knowledge, this is called the Landau gauge. Okay, it's a choice that I make so that my algebra would be simpler. These are things that we have already done, and the Landau levels were given by such an expression. And here n is a whole number. It starts from 0 and goes on. Okay? And in this case, if you remember, my omega was given by E B over M. Okay. So, what's that? Landau gauge. Landau gauge, yes. Okay. So, these are my Landau levels, and if you remember, we have also done something like this. We said, okay, this is like an harmonic oscillator that oscillates about y-axis, okay, and I am unrestricted in x-axis. So the initial wave function that I have written had a form sorry, k. Then I had a function of y. So the kx was given by something like this, okay? And also I have an n because each level can contain up to an n number of electrons in them. So in real space, if I have written this in such a way, let me write it down more explicitly. So now the first condition that I have is that the center of oscillation that I have for my Landau levels must be within Ly and 0. And this also imposes another condition. Okay, so if I, now let me write it this way. So if remember, this was Lb squared times Kx, okay, from the expression that I had for my Hamiltonian that I had written for the Landau levels. Does it make it? Okay, so what I'm going to do is I have 0, then Lv squared Kx must be smaller than Ly. So this one, Lb was defined as square root of h bar over Eb. Okay, then I have my Kx, that is 2 pi over Lx times maximum number of electrons that I can put per each state. Okay, so this is max number of electrons per state. Now, if I write everything like this, I'm going to have something like this. Okay, then I'd like to find a bound for n, an upper bound for number of electrons that I can put per state. So what I'm going to do is I'll write it this way. So I'll move everything to the other side of this inequality. So I'm going to have h. So I combine these two to get an h. And this is the total area of my 2D electron gas. And this is equal to B dot A divided by H over E. And this must be a familiar result to you. So the upper bound for each state that can take is given by the flux, so the surface area of your sample times the magnetic field strength that you apply, divided by the quantum of magnetic flux. In previous lecture, we have shown it in a slightly different way, but this is a more intuitive way of showing. So the only assumption that I'd made, not even an assumption, what I said is that the center of oscillation for this harmonic oscillator must be within my sample, and then I plugged in certain parameters that I already had, then I reached to this result. So per each Landau level, let me get rid of this part. Per each Landau level, I have if I draw, this is my K, this is the energy, so I can start with 1/2 h bar omega, 3/2 h bar omega, 5/2. So it goes with h bar omega separation. And per each Landau level, I have infinite degeneracy. So in each Landau level, I can put up to n electrons, depending on the strength of the magnetic field. So this was one of the results that we got. One final thing that I'd like to remind, perhaps that's somewhat new. Now, what we said previously was this. So if I draw the density of states, and this is my E in terms of h bar omega, then ideally, I'm just like flipping the image up, right side up. So this is 5 and so on. So ideally, what we expect is, let me use a red pen, the spikes, okay? So infinitely sharp Landau levels, but this cannot be the case for real materials because there are various reasons for this. First, there's something called Zeeman splitting. If you remember our first discussion, it turned out that for Zeeman splitting, which was, just to remind you, since the electrons carry spin, they can be in spin up or spin down states in the z direction. And when I apply a magnetic field, the energy of each state will be split by the magnetic moment of each electron times the magnetic field. Okay, so if I have, I mean, this is something you would expect classically. Let's say you have a magnetic field pointing along a certain direction, and then you bring a magnet into this magnetic field. What will happen? Let's say my north pole is here, south pole is here. I put this magnet in this magnetic field. What would be the motion? Can it stay this way? Or, well, it will start precessing because of the force that is applied by the magnetic field on this magnet. Just like the electrons, they are like tiny magnets. So when I put them under the magnetic field, they will, depending on their spin orientation, there will be an energy difference. If you try to force an electron to stay like this, then you have to pay the energy difference. And each spin state, I mean, this is of course a very rough way of looking at this, but will be split by mu SB. And we have shown that for free electrons that are not inside materials, this is exactly the same as h bar omega. But then we said, okay, we don't observe this in real materials. And the reason is we are not dealing with free electrons. The masses that we deal with are effective masses. Then the G factor that we have, which is a sort of a measure of how strong the magnetic moment is related to the spin of the material, is also modified by the material itself. So the end result is we never get this to be equal to h bar omega. But still, the Zeeman splitting, the energy difference between spin up and spin down, results in a broadening or splitting of this Landau levels to a certain extent. Also, the impurities, and I should say thermal effects, result in broadening of these Landau levels. So in real samples, this is sort of what we get. Okay, so this splitting is because of the Zeeman splitting, and the broadening is typically because of the impurities and thermal effects. And the energy difference is 2g mu b times b. We have already discussed these stuff, so I'm just trying to refresh your memories and try to give a different perspective. Now, one more thing that I'd like to mention. Physical significance of what?
That equation, the last equation.
This one?
Yeah, what is
So it's basically telling us that depending on the strength of magnetic field, you'll have certain number of physical states that your electrons can be in.
each Landau level is
For each Landau level, yes.
more opportunities to place our electrons.
Yes. Okay, so now one question that should be relevant to our discussion is that when we can see distinct Landau levels, at what temperatures? Because if you think about it, each state is separated by h bar omega. Okay. And if you also have the thermal motion of your electrons on the order of kBt, and if they're similar to each other, this will introduce a huge broadening, okay? Because now there's a thermal distribution of your electrons, and because of their temperature, and you will not be able to see the distinct Landau levels. So the condition is that the h bar omega must be much, much larger than the kBt so that you can see distinct Landau levels. And I haven't written down anything, but for some samples, you have to go as low as hundreds of millikelvins so that you can start seeing these effects. Okay? So you're talking about really cold, really pure samples here so that you can really observe these effects. Because this quantization of the orbits, if you think about it, really stems from the quantum mechanical nature of the electrons. And this is one of the direct evidences of that. You know, we really have quantum mechanics at way down there. So you need to really prepare pure samples, and they should be so cold that this h bar omega can really make sense for the measurements. Now, I have to introduce a few more concepts before I can proceed with new topics like quantum Hall effect. So we'll go back to quantum mechanics, and I will introduce a notation that will make our lives easier when we deal with the coming sections and equations. So what I'd like to introduce is called Dirac notation. Okay. So in the case of Schrödinger's equation, we introduced a wave function, okay, and we have been dealing with this wave function to calculate certain parameters. But oftentimes, what we have to do is, for instance, if we would like to find the expectation value of an observable, what you have to write down is an integral and then complex conjugate of the wave function, operator for the observable, then you have to integrate this through over all space, or if you would like to normalize a wave function, then you have to again write an explicit integral and so on. So we have to deal with integrations and so on. It turns out that there's a simpler way to express our wave functions, and that way will, at least for certain operations, we can get away without calculating integrals and so on. This is a very broad motivation, but in essence what we'll be able to do is we are looking for a method to express states, and then it will give us flexibility when we calculate certain parameters. So this is just a notation, a new notation, but it exploits the deeper mathematical relations that the wave functions obey, if you like. Okay, so I don't want to go into too much detail, but I just want to give you relevant information so that whenever we use the Dirac notation, you won't be, at least you'll be familiar with what we are doing. So now to represent a state, this is what we do. Let's say there is a special way of expressing states. So this is this denotes a state, okay? And this guy is called a ket. And the reason is what you can do is if you take a complex conjugate of this guy, you write it the other way around, and this is called a bra. So there's a C missing in between. When you bring these two together, this is like a bracket. So this is a ket state, this is a bra state. So you can combine these to form a bracket. Now, one property that, now I'll focus on these ket states. One property that they have is you can algebraically add them. You can multiply with them, multiply them with any scalar. So you can do A plus B to form a new C state, okay? And then you can have some constant, a scalar, or okay? And you can have something like this. Then another property they have, I said this, but I should write this down explicitly. If you take a complex conjugate of a ket state, it will become a bra state. Okay. Then one thing you can do is let's form something like this. Okay. This is called inner product, and then complex conjugate of this guy is just the states reversed. Then there are a few more things that I'll introduce. Now, if I do this operation, actually it corresponds to, roughly speaking, something like this. So this is equal to 1. Okay? So inner product of A, and I am assuming that it's a function of x, this product corresponds to something like this. Then let's say I have an operator O, okay, and it can act on a state. Okay, so it acts this way. Obviously, this is not, if I write it this way, it cannot act backwards in the ket space, so it would always act forwards. So this is not too meaningful as I had written it. Then what you can do is, if you take complex conjugate of both, then this operator will act that way. Okay, so this is in the graph space, this is in the ket space. Then another thing we can have, perhaps I should write this. So if the complex conjugate of an operator is equal to itself, then this means this corresponds to a physical observable. Okay, this is one property of the observables. For instance, if you think about the momentum operator, it must obey this relation, or any Hamiltonian that you write must follow such a relation. Okay, then there are a few more things left that I'd like to introduce. Mm-hmm.
Please show us the result of A.
Well, I cannot because they're not defined, but I will write it down now. Now, one thing we can do is, let me write it this way. So, yes. Of course, I mean. So, now, one thing I can do is, let me first introduce what you asked, and then I'll continue with. So let's say I have an operator A, and sorry, a state A, and then I have a certain operator, okay, and then another state B. So the way I can write this equation is something like this. I have a function, let's say, of x, A star, and I have x, bx integrated over dx. So this means, well, I don't know what this means, but this is one way of showing that. Another thing we can write is, let's say I have A and B, okay? And if you take this guy, this will act as an operator. So I can apply this to another ket space. So what I'll get is something like BC, okay? So this acts as an operator. If you like, I can form an identity operator which will do nothing on. Yeah. Well, this is not identity. This is something else. Yeah, but if you like, we can just do A and A, which will be an operator. Okay. What else? Now for let me see what else I have. I haven't written down any examples. I was thinking if I can find an example, but is there a question? Let me find an example from the book so that it will become more clear what we are doing with these states. Yes?
For example, for the representation of the wave function AX,
Mm-hmm.
we should insert XX operator in between A.
Exactly. So if you have to, I mean, the way I introduce is a rather sloppy way of introducing this, but I don't want to confuse you with too much details, but you're right. If you really want to, so more rigorous way of writing this is that I have to introduce this identity in between. So this will give me something like this, okay? And this corresponds to this integral. So this guy is x prime complex conjugate, then x prime integrated over the x prime. But this is an identity operator, so more rigorous way of writing, I'm going from here to here is like this. But you should already be seeing that this will give us certain flexibilities when calculating certain parameters, because now I don't have to deal with the wave functions themselves, but certain states, and I can get away without calculating certain functions and leave them with a cleaner notation. So this is really nothing more than a notation, but it has slightly more, it can give us slightly more insight about what we will do next. Let me find an example from the book, just to show you. Let's see. Okay, there's. There's not much stuff in this book, so okay, let me do this one. I'll try to explain. So let's say I have a simple system like this. So I have two states, 1 and 2, and this two-state system can be represented with these two vectors, okay? So this is one way to represent a vector. So what I'm doing is that this guy is only a component in x-hat direction and nothing in the y-hat direction, and this one only has a component in the y-hat direction and nothing in the z-hat direction. So I have two states, and there are two ways that I can use to represent. This is a discrete system. For instance, for a simple harmonic oscillator, I would have n such states, and since I have infinitely many n such states, the vectors that I have to form would be infinitely long. So it wouldn't make sense to represent those states with a vector, but since I have a simple thing here, I can represent this with the vector notation. Then let me see what it says. I can write a new state. Okay, so I can write down the linear combinations of these states, just like we have done for the infinite potential well. If you remember, we have written down the general wave function, and then the most general time-dependent wave function was basically linear combinations of each of these states with ENT over h bar. So I had this n, Cn's, and I could write down any function, any wave function, of course not any, but any well-behaving function in this space in terms of Cn's and then these states. And since this is corresponding to a physical system, then I should be able to do the same thing. I can write down a linear combination of, let me write it as A, of these two in such a form. So what I have is, okay, A is a bad way to do it. Let me write gamma here. So I have A1 plus B2. These are just arbitrary constants. So if you like, I can denote this in the vector form as AB, because now this is A0 plus this is 0B. So when I add up these two vectors, I'll get something like this. Then now we can play around with things to show that really we can, this notation simplifies things. Now, for instance, one thing we can do is, let's see. Let's say I am after probability of finding one in this wave function, in this state. Okay, so what I'm going to have, well, that doesn't give me probability, but this gives me the coefficient. So what I'll have is A, 1, 1 plus B, 1, 2. So this product will basically give me 0 because these two states are orthogonal. Just like the wave functions, these stationary states of the wave functions of an infinite potential well. And if you like, it's very easy to show. All you have to do is multiply these two vectors, okay? So 1 times 0 is 0, 0 times 1, 0. So the result will be 0. So you get a 0 number out of multiplication of these. So basically you're taking dot product of these two states with each other. This is one other way to look at it, okay? So if you take dot product between, I mean, this is a sloppy way of writing, but you have two vectors and you take dot products. Since they are orthogonal, this will give you a 0. Obviously, this will give me 1. So this would be the probability of finding 1 in this state. That's a linear combination of these two, assuming that this is normalized. If you like to normalize this guy, then you have to do this and set this to 1. Okay, then you'll end up with that integration, if you like. Okay. No, it's A. The probability that I've written. All right, so this is one sloppy way of showing. Indeed, we can extend, I mean, this example goes on and it extends and writes an Hamiltonian for this system. Then the operator is basically we can show that we can write down the Schrodinger's equation, if you like, in this bracket notation. But I think it's better if we see things as we use them in real examples. So, any questions before we give a break? Nothing? All right, let's give a 10-minute break and then we'll continue with other stuff. Yeah, sure. Thank you.
There was one concept we wrote, I defined it, like if H bar omega will be equal to the thermal motion. So we will not observe any movement or limits.
Yes.
What was the reason I don't identify it?
Because when you have electrons, so what is temperature? It's electrons' average kinetic energy, right?
Yes.
So this means electron is moving around with a certain velocity. But if you think about the Landau levels, they emerge from the fact that electrons take these very well-defined circular orbits.
Okay.
Now, on top of this, you add this chaotic motion that comes from the kinetic energy. So what happens is that basically you destroy that state, you destroy that beautiful orbital. So it just starts doing this random drift motion, okay, because of thermal fluctuations. And the energy scale is given by, so the energy of such an orbital is h bar omega, okay? And if this becomes comparable to the average kinetic energy of the electron, then you destroy this state. It's not a stable, stationary state anymore. There's temperature, there's average drift that starts dictating the motion of electrons, okay? Let me get rid of this. Now, one thing we can do is to solve the simple harmonic oscillator one more time, but this time denote things with Dirac notation. So just this is one example that I could find. So what we can do is, now I have this Hamiltonian, which can be written as such. Okay, I have n omega square x squared. Let's confine ourselves to a single dimension. Okay, then I would like to write this Hamiltonian in such a way. So let me first write it down, and then I'll explain why I do it. So an operator, its conjugate times another operator, and I would like to write it as a Hamiltonian divided by h bar omega minus 1/2. And thus, these operators will be something like this. I have square root of m omega divided by 2h bar x plus ip divided by m omega, and for its complex conjugate, it's quite simple. All I have to do is replace this imaginary number with a minus sign, so x minus ip divided by m omega. Now, this thing is called a number operator. Okay, and it's a conjugate. Now, it's a dagger. Okay. Well, typically it's this is denoted with a dagger. Yeah. So this is like a dagger. I mean, it's. What's that? Yeah. Well, it's the same thing. The reason is that we typically, when you see a dagger on top of an operator, it means it's an observable, and it's typically okay. I'm not going to go into that detail. Sorry, I'm giving you enough details. It's an Hermitian operator, but I'm not going to say that. Okay, so this whole thing is a number operator, and you should already be seeing this because in a way the energy values was something like this: 1/2 plus n divided by h bar omega. So it sort of looks like I divided this energy with h bar omega, put this on the other side, so I ended up with a number. So, but this is not the reasoning. It's just writing this whole Hamiltonian in terms of these expressions. So now this number operator, now let me say n, I'm going to say when it acts on a state of this harmonic oscillator. So we know that there are discrete energy levels in the harmonic oscillator, which corresponds to a discrete state that we can represent with a certain number, and it goes to the infinity. So when this n acts on this state n, it's going to give me a number n. Okay, so basically it may seem like a trivial operator when I operate this on the eigenvalue that I get will be a number that corresponds to the state of that, or number of that state. So if I say n2, then I'll get 2, 2. So, okay. Now, where I'm headed with this is to show, I mean, this is one way of showing how we get the energy values for a simple harmonic oscillator. Now, what I'm going to do is this. I mean, let me also write this down to show you. If I act Hamiltonian on any state, what I'm going to get is something like this: n plus 1/2 h bar omega n, and this is my En for the simple harmonic oscillator. I'm going to show that this is really the case. So what I can do is this. I have my number operator. Let me get some. I think I have a mistake in my notes, so I'm going to refer to the book. Well, I cannot, because I cannot find where it is. Well, I guess it doesn't matter. I'm gonna have to do it. Oh, okay, I found it. So, let me do it this way. Now, what I would like to show you is the purpose of these operators. Okay, so let's do it this way. So I have my n, and then a dagger. So this was a dagger a dagger n. Okay, and what I get from these is I have n plus 1 a dagger n. Okay. So this guy, if you like, is a new state. And it turns out if I do this, a n, then what I'll get is n minus 1 a n. Now let me show you how we ended up with these. Let me see if I have them here. Okay, so now let me do it this way. I just got confused because
Yeah, I think this is a problem. When a dagger applies to the state, it gives n plus 1.
no, this is fine. This is a state itself.
Essential cells on commutation relation.
Yeah, so that's I think what we need to do. So what I would like to show you is how actually this operation. So what I'm after is this, how I end up with an n plus 1. So this, when it acts on an n state, it makes it an n plus 1. When it acts on a n, it lowers it by 1. So this is called rising operator, and this is a lowering operator. And what I can do is I can write down the commutation relation. So I would like to write this down. Okay, dagger. So A dagger minus A dagger A acting on a certain function, let's say. So it turns out that this commutation relation is 1. If you like, we can show that indeed it is true. All we have to do is take this expression. So it's going to give us the commutation relation between x and p. And then with h bars and i's we have here, that commutation relation will cancel. So we'll end up with 1. And then that tells us, that's the part that I got lost, but then let me follow the algebra of the book. So I can write this Hamiltonian as such. So since I have, there's a jump from yeah, but still, I just got lost. There was this one trick that I want to show you. Mm-hmm. Well, I mean, yes. So A dagger A plus 1/2, but this is the thing that I've already written. Anyways, there's nothing wrong with the derivation, but there was one thing that I want to show you, but for some reason I haven't taken it into my notes and I couldn't find it here as well. But this is one other way of showing that indeed this is how we can end up with the energy values, and also that these operators that act on each state can act as a rising and lowering operator. This is one way of showing, solving the Schrödinger's equation, if you like, for the harmonic oscillator. Of course, this is not solving the Schrödinger's equation, but this is a way to find the states without knowing what the wave functions are. But even without knowing the wave functions, we can calculate the energies and so on. By using the relations here, we can actually find the wave functions, but equally valid approach is solving the Schrödinger's equation. So what I want to show you with this example is that the Dirac notation is equivalent to the wave function notation, the Schrödinger notation we used previously. So I'll be referring to Dirac notation as we move on. Any questions? Nothing? Okay. Now, there are two more things that I would like to introduce. These are slightly advanced topics, but I'm going to have to introduce for a clear understanding of quantum Hall effect, as well as we'll be using these concepts, these ideas when we discuss topological insulators and other mesoscopic phenomena that is related to the phase of the electrons. So, first thing that I'd like to discuss is something called the adiabatic approximation. Now, let me write down its explanation first, and then we'll discuss how it is going to be useful in our understanding of certain mesoscopic phenomena. So, it states that the gradual change of the external conditions defines an adiabatic process. So, in a way, the time scale of the external factors are much greater than the time scale of the internal events, then any change that you do on an external parameter will have an effect that we can solve analytically. Okay, so one example that I can give you is, let's say I have a simple harmonic oscillator, a pendulum that oscillates, and if I move this pendulum very slowly from this position to here, what will change? I'm assuming that my motion is much, much slower. I think I wrote it the other way around. Okay, no, that's fine. My motion from taking this pendulum here to here takes much, much longer than the period of oscillation of this pendulum. So, in essence, nothing changes except the coordinate of oscillation. Rather than, if I define my coordinate to be y equals to 0, rather than it oscillating with respect to 1/2 m omega square x square, it will oscillate with respect to about a different point. But if I move it fast, then the force that I apply will affect the oscillation. So this adiabatic approximation, in essence, defines any action that I will make slow enough that it won't affect the overall motion. Okay, so it won't be taken account as an external influence. Rather, it's going to be a very slow change. So let's try to apply this to infinite potential well problem. So I have my infinite potential well, and this is the ground state, 0 to A. Okay, and then I'd like to go from here to here, 0 to 2A. Okay, so what I'm doing is I have a potential well, I expand the wall of this potential well. So what will happen to this ground state wave function if I do it, if I expand the well suddenly? Yes, but right after I expand the well, my wave function will still have this form. Okay, this is, I expanded the well, and this didn't have time to spread out, so still my probabilities, if you like, are confined within this region. So this is a very rapid change. This is not what I'm after. What I'm after is, so this is rapid, is a gradual change. So this A, if you like, is a function of time, and it very, very slowly expands. And it turns out that the wave function in this gradual expansion will follow the boundaries as the walls expand, because we give it enough time so that it can rearrange its energy level to assume this new ground state. Now, and there's a proof which I'm going to show you regarding how we can actually calculate some useful parameters when we make such gradual changes. Okay, so I'll try to show you the derivation of this adiabatic approximation. So now, what's that?
It's opposite with the example you gave before about pendulum. You said that if we move it like gradually, nothing will change.
Exactly. Nothing happens to the ground state.
Oh, yeah, it's same. Yeah.
It's the same. Of course, its shape, you change, it will broaden. But when I say nothing changes, if you take this state, now this is not the ground state. This is not, so this is a stationary state, okay? This is phi 1. And this is a stationary state of the new system, phi 1 prime. But this is not a stationary state anymore. This is a function that I can describe in terms of the wave functions of this new potential well. So to be able to describe this wave function, I have to do this basically, okay? I have to sum over all these prime states. So this means there's a difference between a rapid change and a slow change. By slowly changing my system, I can make sure that it stays in a stationary state, in the ground state, or whatever state you are in. But if I change it rapidly, then I modify the energy levels. I give this enough time to move it around and bounce around, and this now assumes a new wave function altogether. Okay, so thanks for asking that. That's, I guess, an important clarification, important distinction. So now I can write down the initial wave function. Okay, so this is my, let me denote it with I of x. So it's 2 over a sine pi a x. And then the final wave function will be square root of 1 over a sine pi over 2a x. Now, what I would like to show you is how, oops, not this one, how we go from here to here. Now, in this trivial case, it's easy to, write the initial wave function and the end wave function. But of course, as you can imagine, we will not be dealing with the trivial cases. We'll be dealing with much more complicated systems. So the benefit that we'll gain from this is that if we know the ground state of a system, and then if we apply this adiabatic transformation, this approximation, then by starting from the ground state of a simple system and by gradually applying the external influence, we can figure out the end results of the action we take. For instance, I just here physically expanded the walls, but this could be applying an electric field to a system gradually, or a magnetic field to a system gradually. So in a way, what matters is that how my Hamiltonian changes from initial state to the final state. So that's what I'm going to, I'm going to copy it from the book, but what I'm going to prove. So let me get rid of this. And the reason, again, why we are doing this is that we'll apply this to more complicated stuff, but more importantly, I'm going to introduce something called Berry phase, okay, and I'll make a rigorous introduction, but just to give you what's coming up, an insight about what's coming up next, I'll introduce this, and it's basically how geometry and topology can emerge from quantum mechanics. So this is basically going to be a demonstration of such thing. Now let's continue with the proof of the adiabatic approximation. So I have my Hamiltonian acting on a state of the system with such energy, okay? And what I want to do is I want to go from here to here. So now let's do it this way. Now this phi n, the wave function, the time-dependent wave function, I'm not showing the x dimension, will be given by this phi n e to the minus I n t over h bar. This is the old stuff. So in Hamiltonian, now I write it as a function of time because I'm going to do this transition. So my Hamiltonian will change over time, acting on a wave function, which is also a function of time. And it's a trivial dependence, but still, it's a function of time. Then now, I cannot assume that these are stationary anymore because, as we have seen here, energy of this state should change as well. So this will be a function of time again. And obviously, oops, I'm going to write this one. Now, the assumption is this. If I take any state, okay, let's denote n of t, and another state, m of t, if I do this gradual change, they will be orthogonal all the time. And we have a neat way of writing this. This is called Kronecker delta. So if n equals to m, it produces 1. Otherwise, it produces 0. So from now on, I'll express it with something like this. So this tells me that the integral, speaking in old ways, of one state with another should give me 0. And this is something we have seen previously, right? It's something we exploited to get the Cn coefficients. So here what I am saying is that these states should remain orthogonal to each other. So it's an expression of that. Whatever state I have, so I have 1, 2, 3 that goes on, will only change by a phase factor. So these new states will remain orthogonal to each other. Okay? That's a manifestation of that, if you like. Now, what I'm going to do is next this. So I have I h bar. So I'm writing down the Schrödinger's equation. Now this time my Hamiltonian is also a function of time, which we didn't have that before. So I can write any function as such. we have shown that this is the most general solution to the Schrödinger's equation. Okay? N T. And then now I cannot write a constant expression like that, but what I have to do is something like this, and my theta t is now, rather than En t over h bar, it is minus 1 over h bar integral from 0 to t En t prime dt prime. So when I basically solve for this equation for phi t's, what I get is an integral over the Hamiltonian, but when it acts on such a function, it gives me a time-dependent energy value. Thus, this integration will leave me with an integral of that form. So, please bear with me. Get rid of this part. The result is going to be extremely interesting. So now if I plug that expression for the wave function into the equation, okay, this is what I'm going to get. Now I h bar del by del t sum over n Cn of t, phi n of t. Then I have e to the I theta n of t. Okay, so I'm going to take time derivative of that expression. And this must be equal to sum over n Cn of, again, these are all time dependent, h of t acting on phi n of t e to the I theta n of t. So I just basically plugged this equation into the Schrödinger's equation. Okay. Now if I take the time derivative of this part, this is what I'm going to get. I h bar sum over n. I'm going to denote time derivative with a single dot, Cn phi n plus Cn phi n dot. So this is time derivative, okay. Then plus, I take time derivative of this guy, I Cn phi n theta dot n, and I have this overall expression. And again, this is equal to, there's no derivatives here, C sum over n Cn h phi n e to the I theta n. I dropped the time expressions, but they're there, okay? So there, all of them are still functions of time. Okay, now this seems rather complex, but I'll simplify it. So this is something we can write, okay? E to the I theta n goes to n Cn phi dot n e to the I theta n. And the reason is basically if I use, let me see, I can show that if I take this equation, okay, and then sorry, if I take this equation and plug this expression in here, I can show that also this one and this one back into this equation. I can show that this expression is equal to the minus of this expression. So this will simplify things because I have the exact same relations there. So what I'm going to end up with is something like this. So I take sum over n, okay, and Cn dot. Now I'm going to take an inner product with the a different state so that I can find the Cn factors. Okay, so this is what I'm going to do. Let me denote with n and then n. Okay, so with that state, then I have I theta n. Okay, and this must be equal to, based on that relation, sum over n c dot n del mn dot Kronecker delta I theta n. Okay, so all I did is just applied this different state so that I can get an expression for my Cn's. Then now I can write down now I can take, so I'm going to use this in a minute. I can take the time derivative of that expression. So I'll get one more expression to be used in this equation. So h dot phi n plus h phi n dot equals to en dot phi n plus en psi n dot. Okay, so basically I took the time derivative of that. Then again I'm going to do the same trick. So I have n plus m h n dot, okay, and then m n. Since this is just a constant, it's not an operator, I can write it that way, and then en m n dot. Okay. Now there's only a few more steps left. Let me get rid of this. Sorry? It's time derivative. So rather than writing it dCn by dt, I write it like this. There's time derivative here. So I apply the time derivative to this expression. Okay? So at the moment I'm trying to find expressions that I can replace here. So I'll be able to describe my Hamiltonian or my wave function in terms of the changing Hamiltonian. Okay? So it's just basically manipulating the wave functions to get an expression. So first I showed that this equation holds true. I'm going to use this. I take time derivative of this guy and then take inner products with a different state. So next, which one? This one? It's time derivative of this component. So this is a function of time. So when you take time derivative of this exponent, what you get is time derivative of this guy down here. What's that? So this is a function of time.
Oh, okay, so you differentiate it as well.
Of course. I'm taking time derivative of an exponential function. So you take the derivative of the inner thing and then the outer thing. That's what you do. No. Please ask questions. Are you talking about this one? Okay, so let me show you. So what we do is, so this is where it comes from. I'm gonna use h of t, phi n of t equals to E n of t, phi n of t. And then also I have this expression, which is basically written over there, but let me write it one more time. 1 over h bar, 0 t, E n t prime, dt prime. So if I take here, now let me write this down. This guy is E n phi n, okay. Then also I have this guy over here. So let me see. I'm going to have, so let me write it this way. I have sum over n Cn. Then I take it over here, minus ICn phi n theta dot n E theta n. Okay. Then this guy, I can write it as theta dot nt equals to En over h bar with a minus sign. Okay, so also I have ei theta n here. So if I plug that expression in here, I have En. I have one h bar extra from somewhere. Let me see. How did I lost that h bar? So I have I Cn phi n theta dot n. Oh, thanks. Okay, so I have so I took this over here, so I have I minus here, okay, so this is plus, and I have h bar, thanks. And then when I plug this in here, there's a minus sign here, En over h bar with a minus sign. So this h bar will cancel with that one. So this whole expression will be 0. Okay. Then all I end up with is this to be equal to 0, which will give me that expression. then what was I doing? So I have written this guy, and then I'm gonna do this. So I have my M state, then the Hamiltonian, n dot, that's equal to, so now this guy, a Hamiltonian, is an observable, and it must be equal to its complex conjugate, which means it can act both ways, okay? Then what I'm gonna get out of this equation is EM, M, N dot. So here I used it to act this way, or sorry, not that way, but it came from, so I can use it to act any ways I like. So this is what I ended up with. So I can replace that expression with this expression here. Okay, so what I'm gonna get is something like this, M H dot N plus, sorry, let me leave it that way, then En minus Em, because of that expression I moved it over here, so that is the thing, and then I have M N dot. And since this is Mn, if M and N are different, this will give me a 0. So that's why I haven't written it here. Okay? Now, we are very close to finishing. Get rid of this part. Now I have C dot M of t, the time derivative of Cm, must be equals to minus Cm M dot, okay? And this also minus sum over n other than m will give me Cn. So this satisfies the n equals m case. Okay, I'm going to have m h dot n divided by En minus Em e to the minus I over h bar integral 0 to t En of t prime minus Em of t prime integrated over dt prime. So what we are looking at here is how a state, a coefficient for each stationary state will change in time under the influence of this slowly change, or I mean, we haven't imposed anything yet on the rate of change of the Hamiltonian. So this is an explicit expression that gives us how the coefficients will change under the influence of a changing Hamiltonian. Now things will become much more simpler when I do this approximation. So I'm assuming that this rate of change of my Hamiltonian is very small. That's the initial assumption that we made. Thus, I can drop this entire second term altogether because this is a small term. So this drops. So my approximate equation, just give me a few more minutes, please. They'll give us something like this. So C dot m of t is equal to minus Cm m dot. Now I can solve this equation. This is just a differential equation. So Cm of t is equal to Cm of 0, so initial Cm, and e to the I 0 to t. Then I have my m dot integrated over some t prime. So these are functions of this t prime. So it's integrated over t prime. Okay. Now, this means if I start, for instance, Cn 0 equals to 1, which means I'm in a stationary state. There are no other Cn's that contribute to the overall wave function. Then what I'm going to get for my wave function is something like this. Phi n of t will be e to the I theta n of t, e to the I gamma n of t. So I denote this as gamma of t. Okay. And then I have phi n. So this is the time-dependent wave function, and this is the nth eigenstate. Okay, so this is the initial state that I begin with. Now, what this tells us is that if I start from the nth state, I'll only gain a few phase factors when I end up with the new Hamiltonian. And indeed, we can apply this to see that for an infinite potential well, when I change the walls of that potential well gradually, the two wave functions that I have are connected with such a relation. Next time, I'll show you that, and also I'll introduce the Berry phase, and we'll make an introduction, I guess, to the I probably won't have much time left for that, but we'll make an introduction to the quantum Hall effect. Okay. What's that? No, but it's good to have a sense of where it's coming from. Mm-hmm. Yes. Magnetic fields as well, because the expression you have is h bar omega, and basically that omega is EB over m, so you can use very large magnetic fields as well. Typically what people do is very large magnetic fields, very low temperatures, so they use both of them. When Landau first discovered these levels and he quantized, he ignored them because he thought it would be very impractical to have such large magnetic fields over a uniform sample sizes. And then a few years later, he met with an experimentalist and he said, well, it's a piece of cake that we can do it. And then he published his results. All right, so see you on Friday.
minus C and this one.
This one? So now I have, let me see. Now we have this relation, okay? And
So you also put that one 0, yeah? Delta M.
so yeah, this is 0 because I assume that I'm dealing with m equals m. So this is how I get that expression.
I mean, this is
And
also perturbation, yeah? I think this is perturbation.
yes. So what I do is I move this here, okay? And then this mn state, the inner product, is something that I can write from.
You can cancel out maybe these theta's from sides,
Yes.
and then that seems possible.
Then I have.
Yeah, that's possible because here we have mm, so this should be m.
Yes.
Okay. So this should be
Mhm.
also. But how about dot?
Well, let's check the book. Here. So we have this, we put this back into that equation because we have this part. So I put it
there is
here.
a-
Yeah.
dot
Yeah, so from here,
I think you missed.
yeah, I missed the dot here. Yeah, sorry. So that fixes the problem. Okay. Yeah, of course. I mean, I have dot here. I take inner products with m. So this survives from. I swap the, and there's no dot here. Okay.
It was tough.
Well, yes, but I think it's beautiful to see. I mean, it's, up to this part, it's an exact relation, and as you said, this is a perturbative term. So what we say is that it's just this Hamiltonian very slow enough so that its time derivative is insignificant. We end up with a very simple expression. As we'll see, this is, I mean, these two phase factors will become extremely important when we study the motion of electrons. We'll start with a ground state of a very simple thing, and then we'll gradually apply the magnetic field, for instance, and then all we have to solve for is the new phase factors.
Yeah, okay, adiabatic Hamiltonians are very important. But there was one thing, like I was thinking, like I think the idea here also is about this thing that we